Actually, good morning. It's all my fault. Because I have been working for the C++ standards for more than 25 years now. So I voted everything in, except the things I didn't like. There are a few. Who here loves C++? Say yeah. Good. Who here hates C++? Say ooh. Okay, so each time at this talk, when you love something, say yeah. And each time you hate something, say, you got it. Good. It'll be fun. So, we have different standards, different C++ standards, but they are all backward compatible. In fact, C++ is a software project we have now for 45 years. Ooh. Yeah, that's a nightmare, you know that, because we are backward compatible, and we have to be, both regarding the API and the ABI. And the first standard that came out was in 1908, and then we had another technical corrigendum, and then in 2011, the modern C++ area started. And it's all my fault, and I documented all my faults with some books. But these books were not the first books I wrote. Only a few people know that I even wrote some C++ before. And to tell you something about that, what that means, let me tell you how it all began. You are young. Who is older than 50? None. None. Okay, so you might not be able to think about that, but there were times we had no wireless LAN. Ooh. There were times we had no laptops. In fact, when we standardized C++ in the 90s, we did it on paper. So I took some bunch of paper with me, and we went through the pages. And by the way, I learned that the American guys and English guys write the 7 different than the German guys, because I got the task to put page numbers on each of the papers before they got reproduced as a hardware. Reproduce, I mean not virtually on your laptop, just copying them. And I wrote down the way I know it, which looks like 7 in the US. So that was the first time I screwed up the standard, because suddenly page 11 became page 77. And the next time, by the way, that was me in that time. Okay, something's changed. So the other problem I had with my first meeting was the following. So I came up with my 2 German books, which was the C++ standard library. That was actually the first edition, even before the first edition of the English one. And then, with the other book about programming in C++, I put these 2 books on my desk, the way you see it, and suddenly, for the first time, I didn't know him, Bjarne came around and saw the message. Die C++. Who are you, guy? It's a true story. So I had some hard time at the beginning, you can imagine. And I'm always still the devil's advocate here. So I will talk about the traps and not about the good things. But before we start, let's talk about initialization. Ooh. So we learned it all the way that we said, okay, let's initialize an object the way C does. And then we introduced the C++ way, the early C++ way. And then we introduced the late C++ way as an alternative approach, which we call uniform initialization. Which one should I use? Well, with parentheses, some things are screwed up. For example, this is a function, as you all know. And this, as you all know, well, you might not all know, is this valid code? Does this compile? Who thinks this compiles? Who thinks this compiles not? Who is frightened to have an opinion? Who's sleeping? Who only understands Russian? Okay. This is a compile time error. This does not work. So, what's with this? It compiles. Yes, this is initializes an int with the comma operator. And this? It's a compile time error. Of course, obvious. Maybe the parentheses don't work that well, and we should concentrate on the curly braces, but even then, we introduced something new in C++11, which was called auto. So let's initialize an int with auto, which works fine as long as we don't use curly braces. Well, that works fine. Which we standardize to be an STD initializer list, which we make mistakes when we standardize. Yes, we are humans. And by the way, to some extent, it's your fault. Because C++ has no chief architect. This is a community-driven thing. So if there's something wrong, it's your fault that you didn't find it earlier. I will always say that. By the way, that's also the reason we have no consistent design in some areas of C++. So we fixed that, because that was obviously crazy. We fixed that backward compatible, or even for C++11 and some compilers. However, if you standardize, sometimes you have to make compromises. And maybe you know from politics what it means to make compromises. It's not always the best thing to do that. So here's the result. The compromise was, if you use an equal sign, it's still an STD initializer list instead of an int. Wow. An equal sign in initialization changes the type I initialize. We are crazy, crazy guys. So nevertheless, I will pretend use curly braces, but no equal sign. So let's do it. Maybe in the C way, maybe in the C++ way, the old C++ and the new way, but I prefer, I don't mandate, I prefer to use uniform direct initialization, which means curly braces and no equal sign. And the reasons, there are a lot of reasons. It works, it initializes all the types with empty curly braces. It detects narrowing. It now works with auto. It is self-explanatory. If we initialize a vector of 2 int, you can find out where is the declaration here and where's the function call here of an object that is a function object. This compiles even later and initializes a vector v instead of declaring a function v, which would be the case if I use parentheses here. This direct initialization of members in classes does not work at all with parentheses. Initialization of an enum does not work at all with parentheses or an equal sign. This is new, by the way, to initialize an enum with a numeric number. So this is the first thing of C++17. And we can use it for aggregates. So, excuse me, that's my style. We have no agreement on that in the committee or in the community. I apologize. Let's start. Filesystem library. My goal of this talk is to give you some traps. which means I have to explain some things. Who has programmed in C++17 already? Okay, a few. So let's start with the Filesystem library, which we adopted from Boost. I think it's pretty forward readable. You can initialize the Filesystem path and can check whether it's a regular file and then print its file size, or a directory and then iterate over the elements of this directory, or otherwise you check whether it exists or not. What's wrong with this program? You can, by the way, use your old Boost file system code or the experimental file system code and just have to change the include statement and the namespace, and it will compile and it will work well. So look at the middle area here. If we start the program passing a slash for the root directory on a Unix system, it will print out the elements of the root directory in the way you see here as an output. Now let's port this program to Windows. The whole idea of the Filesystem library being standardized is that we can easily port code from one platform to the other. So let's port it to Windows. Here's the output. If we call it for C:\\, the output has 2 backslashes. Why that? Because, as you can see, the paths, if they are printed to I/O streams, they are quoted, which does not only mean you have double quotes around, it also means each backslash is escaped by another backslash, which is not the thing, well, the usual Windows programmer would accept or expect here. So how do we fix that? Print out p.string, so the path.string. And if you want to have double quotes around, add them in your output statement. Can we do something better here? Yes, we can. We have here the problem that performance could be improved, because we are calling here up to 3 times an operating system call for the same file. We check, is it a regular file, then is it a directory, and then does it exist? Here's another way to do that. This is look at the switch statement on top. That's interesting what happens there. 2 things. First of all, this is a new switch statement, something we introduced with C++17, which is that we have the ability, in addition to have the switch condition or expression, that we can initialize something. And here we initialize the path before we switch over its type, which is only one check for the file, and depending on the type, we can then react, and we have only one operating system call. And what you see here already, and that will be the rest of this talk, is the interesting thing of C++17 is not just one new feature and there another feature. The interesting thing is combining different features together. I skipped these slides. So for example, let's combine the new if with the new if with the new type traits and the new lock guards. Okay. Woo? Hey! Oh my God, you didn't get the message. Assume I'm a little bit crazy and want to write a function that inserts something as a string in a container, which I can, in general, say I push back as long as I push back an element that fits with its type to the underlying container. But if I want to have the ability to insert an int in this vector of strings, I need a different implementation of insert as string, because I have to do something different. This int I have to convert to a string. And for that, we have std2string. So the way you program things like that, and there are clearly more smarter and useful examples, you overload different function templates. And if you have a double and you want to insert it, there will still be a problem because the top function is a better match according to the sometimes interesting overload resolution rules of C++. Converting a double to an int is worse than just using it as a template argument. So the first function will be used, and therefore you need even a third overload, and so on and so on. How can we fix that? How can we make it better? So the naive approach would, of course, be to say, well, let's check inside whether this is an arithmetic type, what I have there. And then depending on that, either call toString or just push back the type directly. Unfortunately, this does not work because we get some error message like this. It's self-explanatory. Yeah? Okay, crazy Russians. Good. So what is the problem? The problem is we are confusing compile time features with runtime features. And the compile time feature used here is templates. And we instantiate this template for the type of hello. What is the type of hello? Const char star is wrong. An array of const char, yes, an array of 6 constant chars, and it decays because t is passed by value, it decays to a const char star. So that's the type of x. And for this, the compiler compiles all the code of this function, including the one that will never be called and that will not compile. And that happens with all the options I have, because whatever I pass, either the first then case or the else case is wrong. So we have something new here, which is called if_const_exp, which is a compile time if. And here at compile time, we can now say, at compile time, we specify which part to compile and to deal with. So this works. Either if it's an arithmetic type, the then part will be used and compiled, otherwise the else part. By the way, it does not mean that the other part is completely ignored. It means that the other part, as long as templates are involved, is ignored, your template arguments. So if you call in the else part something that's not declared, this is still an error, even if the else part is discarded. So be careful about that, especially when you come from Visual C++, because they have not implemented that correctly. There's an option, /permissive minors, you can use now in C++ in Visual Studio 17 to fix that. We can make it even shorter. We have a new way to say if there's a type trait, checking whether type T is arithmetic, instead of at the end placing double colon value, we just say is arithmetic v. That's the short fix in C++ 17. So let's now assume we want to lock this vector before we insert something. So what we usually would do, we would say before we insert all these elements, let's introduce a lock guard. And if you declare a lock guard that way, you have to pass a mutex, and in the declaration of this lock guard, you have to specify the type of the mutex again, which is a little bit something we might improve, and we can, because with C++ 17, you can skip the specification of the template parameter of this class, which is called class template argument deduction, which means that like in functions, where template parameters can be deduced from function arguments, we can now deduce class template arguments from the constructor. Yeah? Who likes that? Who hates it? This will change over the next 10 slides. First of all, let's go ahead a little bit with this example. Assume we should not lock the vector the whole time we insert something, because in insert as string, we do some additional stuff, and while we do that, we should not lock the vector. So what's the solution? Pass the mutex as an additional argument. And that means you can pass now the mutex, and the mutex is an argument in insert as string, and we have a lock guard inside the function. Of course, around this, we have curly braces to make sure that the mutex is unlocked the moment the pushback is done. Can we improve that? Yes. This is a way you couldn't write this in C++ 17. Look at that. That's also a new if. That's an if with initialization. Like we have a switch with initialization, we now have an if with initialization. And this even works for if const express, so for the compile time if. So this is funny code because it says we have a compile time condition on the right, but we have a runtime statement, runtime initialization on the left of the line of the if compile time if. And that works. It's fine. So we can write the code that way, and as a lock guard is locked until the end of the if, which is the end of the else, if the else matters. Everything works fine. We no longer need braces around this. Okay, can we improve this code? Well, yes. We can say, let's use a new lock guard we introduced with C++ 17, which is called a scoped lock. And the scoped lock is similar to a lock guard. So the difference is it can accept multiple mutexes, which means we can pass an arbitrary number of mutexes on top of this function now, and then use them to lock them all. And the good thing is, you can now, for example, say we pass even mutexes of different type, like a normal mutex and a shared mutex, which is a read-only, which is a mutex where read-only access can be shared among different threads. This, by the way, uses a deadlock avoidance algorithm we introduced in C++ 11 called stdlock. It's a helper function. So it will try to lock the mutexes in the right order so that you have no deadlock. No deadlock here. The other deadlocks of your code are not solved that way. So people who do this say, okay, I'm smart, but I have no idea. By the way, I should say, and you can even pass no mutex at all here, because this shared lock might lock no mutex, and this code works. It just does not pass any lock. So you can now have an optional way to pass an arbitrary number of locks for code where you need it. People doing this sometimes tell me and say, hey, look at the yellow if const exp condition. Scoped lock LG. Why does it has a name? I can optimize this. I can move the name away. No? Why? Because this is a fatal runtime error, but not the one of the good ones. The good ones have the ability to result in a core dump. This will not. This will simply not lock. Because the problem is that you now create in the initialization of this if statement a lock as a temporary object which is immediately destroyed at the end of the initialization, not at the end of the if. So the moment you call pushback, your lock is gone. Which is okay if you pass no mutex, so then you have no mutex not locked. But that's okay. What do we learn from this? In this single line, we have 5 new features and 1 new trap. And that's a problem we have with C++. Are there more traps with class template argument deduction? Yes. I told you those who like class template argument deduction will think about it in a moment. Here's the reason why. So, these are the constructors of a vector. The declaration of class vector and its constructors. And let's look at the first constructor of a vector, which is possible now, which says, let's create a vector. Let's not specify the element type. Let's pass in curly braces 8 and 15. And can we use class template argument deduction? Yes, we can, because the way this is resolved by a compiler is the compiler finds out which constructor can be called and then finds out whether from this constructor you can deduce the element type. So the constructor called here by language rules is, because it has curly braces and multiple elements of the same type, the last one. So it's an initializer list of t. As the initializer list is an initializer list of int, it's clear that the t is an int. So this deduces to be a vector of int with 2 elements. The same is OK with 1 element. But what happens if I pass parentheses here? Who thinks this does compile? Who thinks this does not compile? OK, you're right. This does compile. It can't call the last constructor, because an initializer list always needs braces. So it must be some other constructor, and the other constructor is the one where the yellow arrow you see. And this is creating a vector of 8 elements of value 15. If you want to do that, then parentheses are a good thing here. Maybe you need a comment here. What is with 1 int passed? Does not compile. Because the constructor called is the one above, the third constructor, taking just the size tn, and there is no t in this declaration, so we can't deduce type t here. Does this compile? Does this compile? Who thinks this compiles? Raise your hand. Who thinks this doesn't compile? Hey, Timur. Those who are standardizing this language should raise their hand here. This works. Deduction works. Because we deduce the type of t here as follows. This is calling the constructor with the yellow arrow, and there's a t. The t is passed as a const reference. And by rule, if you pass const reference, the argument does not decay. And what is the type of an empty string literal? It's an array of 1 const character. So what we deduce is that this is declaring a vector of 1 constant character. Unfortunately, that's an error. So the deduction works, but it will still not compile because you can't declare a vector like that. Are there even more examples? Yes. Let's declare a set of string, and let's initialize the vector with the begin and end of this set of string. Which constructor is called? Does it compile? No? It does. It calls the last constructor, of course. Multiple elements of the same type, and we use curly braces. That's always the constructor taking an initializer list. The problem is, it might not be what you had it in mind, because we pass the begin and end of a set, which means both are iterators, though this vector is initialized by the begin and the end of a set. That's it, 2 elements, both are iterators. What happens if we pass parentheses here? This will not compile. Because the constructor which is used is the one marked with v7, and there we can't deduce type T. But we fix that. We introduced something called deduction guides. And the deduction guides, a little simplified here, with the deduction guides you can say, in case I have declared a vector of taking 2 iters, please deduce that the vector element type is the value type of the corresponding iterator. And with that, you have still, with curly braces, the last constructor called, but now the other constructor works and will initialize the vector v7 by the elements of the set declared before. Great. This is, by the way, the full deduction guide specified. And so let's talk about one more example. What is if we pass 2 string elements here, 2 string littles here? Will this compile? Yes. In initializer list, the type is decayed, so both types are the same. They decay to the same string, a const char pointer, and it will initialize a vector of const char star having these elements inside. So that's nice here. What happens here? This will call the v9, the constructor marked with v9 again, because we have no curly braces, but we have 2 elements of the same type, and that are iterators. And because we have a rule that if these iterators are used, use the element type of the iterator. Well, each pointer is an iterator. So we have an iterator pointing to the element type const character star, const character. So we specify a vector of const char and initialize it with all the elements from the address of hi to the address of world, which is a core dump at best. Try it out. It's really funny. So who thinks class template argument deduction is a good idea? Oh, that's less. Yeah, I think be careful. It's a good idea if you can deduce the type, obviously, but in areas like this, where vector initialization is already complicated, maybe it's better to specify the types directly. Got it? Totally new topic. We have variadic templates. So we can declare a function taking a variadic number of arguments. For example, here, if I have print and I pass 3 arguments, the first argument is passed and deduced as type T, and the other 2 arguments are deduced as 2 additional arguments, and args represents them. That's not a new feature of C++17. That is a feature we introduced with C++11. So this will deduce that we have type T being const character star, because first arg is passed by value, it decays. And then we print out the hello, and then we call print again, and recursively instantiate this now where the first argument type is a double, and the rest is just 1 argument, and then we instantiate this for the first type being an std string, and the remaining arguments is none, so we call print with empty parentheses. People who program that effectively compile code like this because the template instantiation is done at compile time. People who did that said, oh, there's a new operator called Sizeof ... which gives you the answer, how many additional arguments do I have? And if only if the number of additional arguments is greater than 0, I make the recursive call. Does this work? No, because again, we are confusing compile time features with runtime features. All the code has to be valid. Although it's not used, the call of print with no additional arguments, it has to compile if we only pass 1 argument here. This can be fixed now with compile time if. That works now. The problem here is compile time if leads to the effect that we have that we still instantiate a lot of template code here, which takes a lot of compile time and resources. So therefore, we introduced something new in C++ 17, which is even better, which is called fold expressions. So you can, if you have an arbitrary number of arguments, so what we call a parameter pack, a variadic template, then you can say, do something with all the elements in this template, in all the arguments here. So you here see the expression. If I have an arbitrary number of arguments for fold sum 1, the new expression is in parentheses with 3 dots, then the operation, then your name of your argument where you apply this, and this will expand to combine the sum of all the elements passed here. So if you pass 2 of them, you will compute 17 plus 4, and if you pass 3 of them, you will compute I plus 1000 plus I, and as this is generic code, you can pass a string, and this will compute string high plus high plus high. As long as this is valid code, the fold expression will compile. If you pass nothing, this will not work. But there's another version. You can have an initial argument here, saying initially there's 0, so which says, as before, we can build the sum of 17 plus 4 plus 0 and the other expression. But now, fold sum can be empty. Unfortunately, it can no longer pass a string because 0 plus the string high does not compile. Good. Why do I tell you that? We come from the point where we said we have this recursive application of the variadic template. Whether we use compile time if or not is not that important. We instantiate templates here recursively. So can we do better? Yes. Let's just take all the arguments in this function and print them out and write them to stdc out. And that's a fold expression here. This code will print all the arguments because it effectively compiles that we first print the first arg, and then the second arg, and the third arg. We send them all to cout. The bad news is no spaces between the arguments. While we can add something behind this expression, it's not allowed to put something inside because the syntax of this fold expression is exactly as you see it here. You can only apply 3 arguments. Well, in the middle there has to be 3 dots if you have an initializer, and you can only apply twice the operator you want to combine. So you can't say this expression in addition prints out a space or something like that. But we have C++. We have ways to do that. So what do? Well, we implement a function called, before we print out something, we print a space out. And that we can use here. We can say, now send to cout all the arguments passed here as an argument, except the first one, because for the first one we don't want to have a space before. And this will print high 70.7 world, because this expands to the following code being compiled. Now, this code is nasty. There's a trap in this code. If you program the thing on the right, the yellow expanded template code, before C++ 17, you have undefined behavior. So look at this. Just write this code. Before C++ 17, you have undefined behavior. Why that? Because it's not clear when space before is called. Space before might be called twice before we start with the first output. So it might be that the output is high space 7.5 space world, But according to the rules of C++, before C++ 17, there's another option that this is solved, and that means the compiler decides first to call space before for 7.5, and then space before for world, and then start with the output of the results, so that we have two spaces there. And that's a real problem. We fixed that. We have, in fact, and not many people know that, we have new evaluation rules for C++ code in C++ 17 to fix problems like this. So here we have the list of the new operators. Not all of them, but some of them have new rules that they are now guaranteed to evaluate from left to right, like the dot, like the output operator, and the equal sign from right to left. So that means it's now guaranteed to work that we can use this example in C++ 17. But by the way, we didn't standardize a general evaluation order. If you call a function, and inside the function you have arguments calling space before, then the evaluation order is still undefined, and you might get here 2 spaces before the elements are written. Okay? Good. There's another interesting thing with fold expression people don't see, which is when we use fold expression or when we use variadic templates, we could pass all the passed argument. Like here, we could say for all arguments passed to call foo with them. We could even have expressions here. We could say for all arguments passed to call foo, pass them doubled. So added to it themselves to foo. But we could not say something like this, call foo for each of the passed arguments. We have now the ability with fold expressions to do that. It looks like this. This is using the comma operator. So what we have here is, you say, let's combine calls of foo for each argument and combine this with the comma operator to make it one statement. That will be very, very powerful in code for variadic templates. And of course, we can use that in our example. We can say, instead of calling space before, we implement a lambda that prints out an argument with a space before, and we combine these calls with the comma operator here. Is this all? No. Of course, we should specify which separator we use here, which by default is a space, so that we can say, beside calling print for some arguments, and inside there's a space, we print another character between the arguments. And there's a new feature in C++ 17 you should also know, which is template arguments now can be specified to have the type of auto. And that means we don't specify what the non-type template argument, what type it has. So every type allowed is possible, which means we can pass characters, which is also the key fold. We can only pass 42. Then between all the arguments, we have 42. Very useful application. Or we can pass a string. And there's a new way now to specify a string. We no longer have to define it outside the function. We can have a string literal defined with no linkage. That means inside a function, right before the template call, you can have a static const char initialized as a separator you want to pass here, and that compiles. So that way, we can use this template now to print all the arguments with comma space between. Again, you see, a couple of different features are combined here, 3. And for those who love to have everything in one line, this is the whole thing in one expression in the middle of the function. Here's another application of deduction guides, by the way, just in case you know it. For those who are lazy to count arguments for std array, we have now a solution. We have a deduction guide saying if std array is initialized by a couple of ints, the deduction guide says, let's take the first int t to deduce the type of the elements, and as a second argument of the template, let's then deduce the number of additional argument, that is the size of dot 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 operator, plus 1 for the t. And so we can deduce, this is an array of 9 int. Yeah. Now you're back again to like it, yeah. So, however, what happens if we have here different types in the elements? We discussed that. We discussed whether we use something called common type of all the elements, but we decided not to allow that, or not to allow that yet. The standardized deduction guide, which is in the standard here, is as follows. It says, this deduction guide is only enabled as valid code if the first type t is the same of all the other past types. And that is a fold expression, which says, let's combine with AND the expression to check whether type t is the same as all the other types, u1, u2, u3, u4, and so on. So therefore, the first thing will compile, the second one not, the second line not. Whew. Do you like C++ 17? I don't do a good job. Something completely different. Assume we have a vector of string. And this vector of string is initialized by a couple of values. In fact, id lowercase plus a number, followed by id uppercase plus a number, and then that as a loop. So id 0, id 0, id 1, id 1, etc. are the elements. Now assume we want to sort these elements. So you can simply call sort for that. That works, and it would sort according to the string sorting of less than, which would mean that all the lowercase IDs would be in front of all the uppercase IDs. Now assume you want to sort it a little bit different and say, let's ignore the first two characters and sort them then. How do we do that? Well, we can pass a lambda saying our sort criteria is when we compare two strings, we ignore the first two characters by only comparing a substring starting with the third character of this string. That's okay. That compiles, it works. Here are some numbers. On my laptop, for some 100,000 elements, we have some duration. Think about this as, I think, milliseconds. And you see that we are getting a factor of more than 2 slower. And it could be worse if the strings are longer and need memory inside. The reason is that substring creates a new temporary string, and this temporary string has to get initialized, and then we throw it away. So is there a cheaper way to do that? Yes, there is. It's called string view. String view is a view on a character sequence without owning the memory, so the character sequence. And what we can do here is, let's just create a view to the elements, and in this view of the elements, we ignore the first two characters. And suddenly, we are even faster than the ordinary sort. This is not a proof of the numbers, by the way, but this is where it goes to. So, you might say, awesome. Who thinks this is awesome? Yeah. This is a string view. And string view has a hype. Has a hype. There is something you have to learn now for the rest of your life. Underscore view is evil. Say it with me together. Underscore view is evil. Next 2 weeks, you say it every morning. Because a view has the danger of a pointer, which is worse than the danger of a reference. Why that? Well, what a string view does is the following. Assume we have a string literal, and we pass it to a function, so to some place where we need a string. What the string does, it creates a copy of the string literal. Whether it allocates memory for that or whether it places it inside the object depends on the length of the string. But you create your own object with its own data, with its own copy of the string literal. So you, by the way, compute the length, allocate memory if it's not too short, the string, and then you copy the characters. What a string view does, it does not own any memory for the value. It only owns the information necessary to keep this character sequence as looking like a string. That's even possible to say a string view is created from a string. Because we say, yeah, we have a view to this, and that's what we did with the sort function, to say we have a view to this string, but from this point of view, we just point to the character sequence inside the string, so we can ignore the first 2 characters and do things like that. The point is, the first example, creating a string view from a string literal, is not a problem because the string literal exists the whole lifetime of your program. But if you create a string view from a string, you have to be aware that the string view does not outlive the life of the string. And especially careful you have to be because there is an implicit type conversion from string to string view. We decided to do that because creating a string view from a string is cheap. The other way around is expensive, so that's an explicit conversion. So what can happen? Somebody creates a string view, cheap, safe, representing the character sequence high with a string wrapper, string API. Then somebody writes a cool function adding one string view to the other, which we don't have standardized, but it's possible to have it. And I think it's okay. The only point you have to be aware is that the return type is a string, because now you have 2 views to a string, and now you create something new that has to exist somewhere and store the memory somewhere, so you return an std string here. And then in your project, somebody writes a cool template. The cool template looks like this. Let's compute the sum of 2 arguments. So let's take an x of type t, let's take a y of type t, let's add them and return the sum as a t. Looks perfect reasonable for most of the people, because int plus int is int, string plus string is string. So where's the problem? Well, the problem is we call this function for our string view. And what happens is, inside sum, we compute the concatenation of the 2 past string views. So we compute string view high plus string view high, which creates a new temporary string. But then we return in the template the object as type t. And what is type t? String view. So we create this, and we leave the function. Bingo. No compiler warning, no compiler error. That's the danger of views. Got it? So you see it later, if you're lucky, you have a core dump before you deliver your code in production. By the way, who has made a mistake here? Who did something wrong in this code? The author of sum is somebody called. So what should they do? Return type auto. There's a reason we have a return type auto. A lot of people have in style guides don't do it. There's a reason. The reason is not only convenience. The reason is templates know it better than you, what generic code does. So if you pass two string views and the result of plus is a string, then it's a good idea to declare the return type to be a string, which will be the case if you use auto here. And if you inside have this expression, please do the same. Inside, use auto here. So auto, as a return type, is very important for generic code. And it's not convenience. It helps to avoid some traps like this. So let's go back to our example. Well, we have seen the danger of string view. So keep in mind, if you use string views, feel as uncomfortable as using raw pointers. But if you are convinced that this code is safe, use it. And which is fine in this code, saying I convert the existing string to a view, then I use substring, and then afterwards the view is no longer there. That's a cheap code, and therefore this works fine. Can we improve that even better? Oh, yes. We have now parallel algorithms in C++. So we have the option to pass an additional argument which can say, let's compute this sequentially. But it can also say, let's compute this in parallel. And if we do this in parallel and we run this program and we measure again, you see something like this. Again, the numbers depend on your platform. But you see that now finally the number of the last version is even better, more than twice than the initial version, the initial sort. Parallel STL is a new feature. It's unfortunately only available in Visual C++ yet. Standard conforming. But it's cool. But it's interesting. And there are some traps to discuss. So, for example, one common trap is this. Let's accumulate. Let's use accumulate. What does accumulate do? It combines all the elements of a container. And by default, the combination is just to add them so that you get the overall sum of all the elements. But there are people who say, let's do a different way to deal with the elements I have. So look at this example. I have here 10 times inserted in a collection the sequence of 1, 2, 3, 4. So in my collection, I have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 10 times. And my operation I pass to accumulate is this. Some people do that. And they say, well, this is not just combining the sum of the elements. This is when we iterate over the elements, we take the previous elements and add the square of the new element, which in fact means that we compute the sum of all squares of the elements. So as the square of 1, 2, 3, and 4 combined is 30, if we have 10 of them, the output should be 300. We don't have a parallel version of accumulate, because accumulate requires, it is specified that it goes from left to right. We can't parallelize something that computes one element after the other. So we have introduced something new here called reduce, and that does more or less exactly the same as accumulate. So let's use reduce. Let's call it in parallel. And yes, we get 300. Great. So let's extend the test. Look at the 10 on the top. Let's do this for 1,000 elements. Accumulate and reduce. Both give you 30,000. Great, works. OK, one more test case. Let's switch to 1 million elements. Oh. Now we have different output. Oh, switch back, switch back. Switch back to 1,000 elements. Panic. Oh. But wait a minute. Just before it was 30,000. And now it has a totally different output. What is programmed here? Well, in fact, if you run this a couple of times, you get some interesting numbers. So it seems we have no longer code where you can predict what happens, even if it's crazy. I mean, if it would be all the time 28316,430, fine. But here we get different results on the same platform just by running it again. What is the problem? Well, the first problem is don't do this because you have a non-commutative operation. And that's a requirement for reduce. It's not a requirement for accumulate, so for accumulate this is fine, but not for reduce. There might be something wrong. But why isn't there always something wrong? Well, the answer is parallelization might depend on your load of the CPU. In fact, the implementers of this library are free to decide how many threads they start on what approach they ever have. It might depend on the number of elements. It might depend on the CPU load. It might depend on the size of the moon, whatsoever. So beware of this. Do it right. And if your test case runs, it's not a proof that it will always run the correct way if you violate precondition of parallel algorithms. How do we program that? Well, accumulate is fine. Here's a lambda inside. The lambda that computes the square of all elements. How do we program that in C++ 17? We have just for this reason introduced a new algorithm called transform reduce, which is a combination of a transformation of each element and then accumulate that. And that way, the underlying threads can parallelize however they like. They can in parallel compute the square, and then the operation to combine the results has to be commutative. So this works and gives you the correct result. This will be one of the most important algorithms we will see in future of C++. It's in fact something we have everywhere, like called map reduced. It's our map reduced. Yeah, we like that. And by the way, we have class template argument deduction, and we should initialize with curly braces. So do it as you see there. You can just use std plus with empty curly braces. That compiles now. Yeah. Good. I'm a naive guy. I'm not a good programmer. My benefit, I ask all the time until people get crazy, and then I document so that I remember it later. That way, I can explain this or write books. So, of course, when I saw this, I said, OK, but why the hell do we have parallel versions of this? So this is partial sum. Partial sum computes the sum of all the previous elements. So if you put it, apply it to a sequence on top. You see that the first resulting element is 3, because it's just 3, and then comes 4, because it's 3 plus 1, and then 11, 3, 1, 7, etc. So we have the partial sums, which to some extent means we convert relative values to absolute values. It's something you need in a lot of places. The interesting thing is we also have a parallel version for this, which is called inclusive scan. So I'm wondering, how can this be? How can we compute from left to right all the partial sums and get this parallelized? Because this looks like it has to be sequentially computed from left to right. Those of you who know a little bit about parallel algorithms know that this was a very naive question of me, because there are algorithms how to do that, and this is the way you can program that internally. So this is a sequence, the source sequence, just with some additional numbers that you see the general way this algorithm works. So you have to do 2 steps, exactly 2.5 steps, to compute or to convert this to a sequence of the absolute values. The first sequence is you always combine the sum. So first the sum of the first 2 elements, then the sum of the first 4 elements, then the sum of 8 elements, and then the sum of 16 elements, and so on. And note you don't need any additional memory. You can do it in the memory you have. So what you in fact do, you have something like a binary tree always computing the sum of the elements, but without any additional memory. Then the rule is, the half rule is, place a 0 at the end. And then we go down as follows. We move the thing on the right to the half, to the previous half, and we combine the sum of the previous half and the new half, as you see with the blue arrows. And the point is, this all can be done in parallel. So multiple threads can do this in parallel, and at the end, you get the sequence of absolute values. This is not invented by me, of course. This is known in the community of parallel algorithms, and it works very well. The Intel guys who did a lot for the parallelization of STL find incredible improvements in speed with this algorithm. So it works even in places where you think sequential processing is the only option. Good. I think we are coming close to the end. A few more examples, again, combining some things. Structured bindings and PMR. If you create a vector, each vector has an allocator. In fact, what you declare is an object of the type T, and allocator being by default a standard allocator, and it is initialized by your initial values, if any, and the last argument being an object as the instance of this allocator. With my style, I would use curly braces at the end. Okay, this is the object. The vector asks for memory. So when inside the vector needs some memory, it calls for this object allocate, give me some memory for this amount of elements, which then calls by default the global operator new, which then by default calls malloc. And you can intercept and do something different here. Beside replacing the operator new or replacing your malloc library, you can provide your own allocator and say, whenever this object needs more heap memory, I do something different. There has been a lot of different approaches to use this feature. In fact, you don't know that, but for those who are very old, this feature was originally introduced because under Windows, pointers had different sizes, raw pointers. And you had something like a near pointer and a far pointer. And we had to deal with both cases, so we needed different types for the way we use memory internally. These times have gone, mostly. And now we use it to say, let's use different memory models. So let's go to a program where we just place some elements in a vector. And by just declaring a vector of a string, of strings, if you look at that and run that, you might find out that this is about 1,018 mallocs for 134,000 bytes, depending, of course, on some implementation details. What you can do now instead, you can say, I don't want to use heap memory here, so let's allocate some memory somewhere else. Or let's allocate it in a head on the heap. However you do that, or in your data segment, as here. As you say, let's, for example, declare an std array of an std byte. Std byte is a new type of C++17, where we say this is just memory, to not fall into the trap that we compute with numeric operations here, with the element type. So we have 200,000 bytes here. And then let's create a memory pool, initialized with this array. And then let's use a vector initialized with this memory pool. And this vector has a special type. It's called a PMR vector, polymorphic memory resource vector. Let's compile this again and find out. Now we have only 1,000 mallocs, only for the strings inside, but no longer for the vector. The vector uses the memory of this array. And the funny thing is, when we leave the scope of this pool, the pool will free the memory and we can reuse it later. So let's use it again, and let's use a vector of PMR strings, which is strings when they use heap memory. They might use a different approach. And the funny thing with PMR is that the vector can tell their elements where to store the memory. That's the polymorphic approach here. So the type, in general, as a PMR string would in general allocate the memory on the heap. But in this case, it will allocate the memory wherever the vector tells it to do. So what do we get? 0 mallocs for 0 bytes. For embedded system people, this is awesome. I have one project where they say, oh yeah, now we can use a vector in embedded systems that cannot at runtime allocate heap memory. And this helps in a couple of places. For example, if you have a balanced binary tree and you initialize it with some strings and you iterate over them. Well, first of them, I have to say something here. The for loop iterates over the elements of a collection, which is a pair. The elements are pairs of constant longs. You are not allowed to modify the key because you would screw up the sorting in the binary tree, and a string. And then you have to use first and second to access these elements. That we first can modify as follows and say, let's use what we call structured bindings. So let's give them better names, the elements of the pair. So let's iterate over the elements, but the elements there should be named key and value instead of first and second. And now let's use it in that loop. And that code is, of course, a lot more readable. So if we do that, and we run this, we will find out that the elements are spread all over the heap memory, because each time we place a new element in the tree, they allocate some memory in the tree. And here you see the distance of different elements in this tree, which means if we iterate over all these elements, we jump back and forth between our heap memory, and depending on the cache size, you might get cache faults, page faults, and that means you need more time than necessary. Can we fix that? Yes. Polymorphic memory resources. So let's use one of the pools. There are a few with different abilities. Here I use a synchronized pool resource. I use a map with a PMR string. And this pool resource is used as my heap memory in my map, also for the strings inside. And what I see is that the elements are located close to each other. The only reason the distance you have just in the middle of this algorithm, or after 3 elements, is that it initially didn't allocate enough memory and allocated some more memory somewhere else, which you, of course, can specify before. So that way, we can make sure that even in a binary tree, all the elements are located next to each other, which also is something that helps computing and performance. There's a trap here. The trap is this move is no longer a move. Because if you create a string, it allocates memory on the heap. Now you say, I don't need the string anymore, so I move it into the vector of PMR strings, but the PMR strings use the heap associated with the vector. So they use a different heap, so you can't move the normal heap to this pool memory. So this move becomes a copy, and that means it might throw. In fact, we fixed the specification of the string to say that we have there might be an exception if you have a move operation for strings using an allocator, and for the assignment operator, it's even more complicated. We say it might happen that the assignment throws if the allocators used in the strings are not interchangeable. That's what is written here. This is a very, well, you had this last category in your slide, which is the bottle with the fire. This is crazy stuff just for library experts. We call this POCMA, propagate on container move assignment. And that's some way to find out whether allocators can exchange their memory. And if not, this might throw. If they can exchange the memory, the move is a move here. Good. Okay, last topic. 10 minutes left. We have optional. We have used it from Boost. So optional string is now standardized. Finally, it should have come already in C++ 14, but we had some things to discuss. Who's used optional already? A couple of people, okay. The feature is clear. You say, I have a string with some value, or I might not have a string at all, which is a different state than having an empty string. And you can assign a value, or you can have no value. With if, you can check whether it has a value. With star, you can access the value, sometimes with a check whether there's an object, or sometimes not. Good. Optionals have an order. So you can use them to sort. And the interesting thing is, you can even compare them with the underlying type. So optionals can be used with a less than operator directly with elements of the underlying type. That means you can do something like this. Let's create an optional bool. And now let's check whether this optional bool is less than false. This is valid code because by definition, having no value at all is less than any value. So we can put these elements in a set, for example. But this is maybe a little bit surprising to people. And same if you say, I have an optional unsigned, it makes sense to check whether the optional unsigned is less than 0. Which means I have no value at all. There are better ways to do that. You can just say if UO, or if UO has value, but it's also possible to do it that way. And by the way, the way we deal with this problem was the reason the adoption of optional from Boost did take until C++ 17. We were discussing, should we protect you programmers from this craziness of this code or not? We decided not to do so because we already have a problem with an optional bool. I mean, that's 3-state object. Maybe we should have a different data type there. Maybe not. There's more about that. So if you have an optional bool initialized with false, then not optional is false, but optional equals false is true. And if you have a pointer inside, not optional is different than checking the optional against the null pointer. So beware. I told you so. And there's another interesting problem we run into when we use optional, and I saw this in some code. Let's have a function returning a vector of int, and then finally decide, oh, it might happen that we don't return a vector at all. So let's switch to say get vector returns an optional vector of int. So let's use this range-based for loop and change it as follows. Let's iterate over the values of the returned vector. Value will throw if there's no element, so then is an exception. But if there's no exception, this code should be safe. But it isn't. Because this will iterate over a deleted return value. Why that? Because it's always a problem if you use a range-based for loop, and on the right side, you use a getter accessing by reference a temporary object. Because inside the range-based for loop, this is expanded to the following expression. Let's first initialize a reference, initialized by the thing on the right of the range-based for loop. So get vector.value. Now you might know that a reference extends the lifetime of a return value. But the return value is a reference here. It's not the temporary object returned by getVector. So yes, RG will extend the lifetime of the reference returned by value, but the underlying object is deleted already when the loop actually starts. This is a general problem with the range-based for loop. For this reason, in some companies, there's some warning about using the range-based for loop. So be careful. This is not only a problem with optional. I can create these examples with other types as well. So beware. Final example, variant. A variant is a new type of union. You can say my object contains 3 different types, but only one of them at a time. So for example, here my objects contain an int, a long, and a string. And the good thing is, a variant knows what it contains. So here you can ask, what is the current alternative? We call this alternatives we contain. So here, because we use a default constructor, which uses the default constructor of the first alternative, the first value is 0, and the index is currently 0. And when we want to get access to it, we can ask for the value of the first alternative or the value of the alternative int. And once we assign a new type, a new value with a different type, just overload resolution is used to find out which alternative is used here. The best match is used. The best match here is std string, so we set this variant holding and representing a string. And we can later on assign an int or long, and it will work. Good. Why do I tell you that? Because if I give you a talk about C++17 only talking about traps, I'm getting killed if I don't end with something positive. And the positive thing is, variant creates a new way, a totally new way of programming polymorphism. You might know that or learned that the way we program polymorphism means that we have a base class with an API and then virtual functions, and so that we can create objects and use them later on. And especially that we can create inhomogeneous collections. The problem with this is you have to use pointers. So you have to use new here in the function createFig, and new line, new circle, and that's a nightmare. You can use unique pointers, you can use shared pointers. Shared pointers have their own problems. Unique pointers are a lot better, but they also have problems. For example, downcasting with a unique pointer becomes interesting. So yes, there are some issues, and we have some workarounds for that. We have more smarter pointers than raw pointers, but the principal problem remains that we have to use pointers in one or the other way. How can we do it better? By the way, and that means don't forget to delete the elements before we remove them from the vector. How can we do it better? Use variant. Say my elements in my vector are either a line or a circle. The cool thing is a variant has value semantics, being either one alternative or the other. And that means you don't need new anymore. You can just add, push in a line or a circle just initialized with the corresponding values. And then the vector will copy its element, and copying the elements which are either a circle or a line will copy them as a circle or as a line. Now, how do you use polymorphism there? For that, you use visit. Visit is your polymorphic call. You use a generic lambda, and this will be compiled for all different types used in the variant. And the visitor will then decide at runtime which one of them to call. If some of your types does not support draw here, this visit call will not compile at all. And it will have the same speed as a virtual function table. So this is your local virtual function table. If you measure that, this is as fast as before, but not having new and delete here is a lot safer and a lot faster usually. And you don't need base classes, you don't need virtual at all. So we have a new way to program inhomogeneous collections, which I think now whether I should teach them first before inheritance. That's the problem now, what to teach first. So one last thing here. Can we downcast? Yes, we can. There are a couple of ways to do it. The first way is, if you have your circle and you have a specific member called getCenter and you want to call this for the circles, well, if you iterate over the variant, downcast them as follows. You see here the code for a variant. There is a getIf circle for the address of it. This is like the dynamic cast for variants. And here again, we use the if with the initialization. And if this is a circle, we call getCenter. Is there another way? Yes. We can, inside the visitor, say, if this code compiles only if the type of object is a const circle reference, then call getCenter in addition. Is there a third way to do it? Of course, this is C++. We can overload different lambdas. We can say there's a general rule for all the types using auto, and there's a rule for circles. How is this programmed? What is this overload here? Well, it's easy. It's this definition. Okay. First, look at the bottom. This is a deduction guide saying if I have an overload initialized with some data types called functors, then deduce that we have an overload template using these functors as arguments. And then take, on the line above, take these arguments as base classes. And then from the base classes, derive the function call operator. So what you in fact create here is something like this. Easy, huh? Well, you don't have to understand that. We might standardize it. Actually, we discuss whether we make it a language feature. But this is interesting. That uses a lot of C++17 features again. Variant, aggregates with base classes, deduction guides, variadic using, which I didn't introduce yet. And a last comment about this. Don't even think about initializing overload with parentheses because it won't compile. This is an aggregate. And the good thing with uniform initialization is that braces always work, and most of the time as you want it. You got the message? Good. You have seen a lot of cool new stuff, I hope. Here's a list. But what I did is I did tell you how to combine these features, and both for single features and the combination, there are traps you should know. So beware about it. And C++17 is a lot more than I thought. My book currently has more than 400 pages just explaining all the features and the traps of C++17, which is a book now covering both language and the library. There's a gift to you I can give you here. For 1 week, you can get this book for free. It's not done yet. Not for free, for almost free. It's an ebook. It's not finished yet. There's a special price now for this week. With this code or with email, web address, you will get it for a very reasonable price. If your company pays, please pay more. I do it for a living. Thank you very much.
So, Nika, thank you. And we don't have time for questions here. And Nika will be available in the discussion zone. So, if you want to ask him for something, you can do that in the discussion zone. Thank you.